Comparison test. We know that the series 1 over n squared converges because it is a p-series with p equals 2. What about the series 1 over n squared plus 1? It looks so close to the series 1 over n squared, but not quite because of the plus 1. It is not of the form 1 over n to the p power. We can only guess that this series converges also. Certainly, we can use the integral test to check the convergence of this series. The a sub n term is 1 over n squared plus 1, so the function f of x is 1 over x squared plus 1. The derivative is negative, so this series is positive decreasing. We evaluate the improper integral, taking the limits at t go to infinity. The entire derivative of 1 over x squared plus 1 is tangent inverse of x. We plug in t and 1. We see that this is pi over 2 minus pi over 4, and so it is pi over 4, which is convergent. And so by the integral test, the series 1 over n squared plus 1 also converges. And so if we were to guess that this series converges by looking at the p-series, our guess would have been correct. Observe that n squared plus 1 is greater than n squared. And so 1 over n squared plus 1 is less than 1 over n squared. So certainly the series 1 over n squared plus 1 is less than the series 1 over n squared as n go from 1 to infinity. And we know that the series on the right is the p-series. It converges. That means the sum is finite. But the series on the left-hand side is less than the series on the right-hand side. And so the series on the left cannot be infinity. This line of reasoning is called the comparison test. It is much shorter than the integral test. The comparison test states that if there are two series where the terms are positive, if b sub n is convergent and a sub n is less than or equal to b sub n for all of the n after some n terms, then the series a sub n is also convergent. If the series b sub n is divergent and a sub n is greater than or equal to b sub n for some n terms, then the series a sub n is also divergent.